In this video, we're going to look at LU decomposition, which is the main part of solving linear systems. And here you see a linear system with 3 equations and 3 variables. And in matrix language, we write it as AX equals B. And A is then a matrix, a 3 by 3 matrix. And X is the unknown solution vector. And B is the right-hand side, which is 16, 44, and 78. Now, if we have written the matrix as the product of 2 matrices which have a simpler form, triangular matrices, then it becomes easier to solve that linear system. L is a lower triangular matrix. It's the matrix with 1, 0, 0, 2, 1, 0, 3, 2, 1. And you see it has zeros above the diagonal, meaning that Lij equals 0 for all I less than j. An upper triangular matrix, of course, has the zeros below the diagonal. And then LU decomposition is just finding L and U. So given a matrix A, find an L and U so that their product equals A. And we will assume that L is a unit lower triangular matrix, and that means that it has 1s on the diagonal. We could have chosen U, but in this case we'll choose L. And then, if I want to solve a system AX equals B, having the L and the U, it's like solving L times U times X equals B. And then if we call UX, if we call that Y, then we are solving first a system Ly equals B, and then Ux equals Y to get X from B. And these systems are much easier to solve. On the top, you see the system Ly equals B. And since it's triangular, we can already find from the first equation that y0 should be 16. And then if we have y0, we can substitute it in the second equation. So we subtract 2 times 16 from 44, and then we get that y1 should be 12, and so on. For u, we start at the end. We do a backward substitution, because we see that 3x2 should be equal to 6. So x2 equals 2. x1 then equals 1, and x0 equals 0. And this way we have solved our linear system. Now we will derive an LU algorithm. And we do this starting from just the multiplication of 2 matrices L times U. And we can write that for every element, Aij equals R equals 0 to n minus 1, assuming that we have n by n matrices, and then we multiply LRIR with URJ. And we can use now the fact that L is lower triangular, so assume I is less than or equal to j, so we're looking above the diagonal or on the diagonal, then this can be written as Aij equals the sum from R equals 0 to I, L, I, R, U, R, J. Because if R is larger than I, this element becomes 0. And we can then write this slightly differently. R equals 0 to I minus 1, L, I, R, U, R, J, plus L, I, U, I, J, where we have separated out the term with I equals R. But then we can use the fact that we also assume that L is a unit lower triangular. This equals 1. And we can write it slightly differently with uij equals aij minus the sum r equals 0 to I minus 1 aij. We need the LIR URJ. So this is a formula where we can compute a new uij from the original aij and previously computed L and U elements. And if we assume that I is larger than j, we can do something similar, and then we get an Lij equals 1 over ujj, and then aij minus a similar sum. Then we do up to j minus 1, LIR URJ. So this gives a formula to compute the elements of the lower triangular matrix, and we only need to compute those below the diagonal, because those on the diagonal, they are 1. And here we have to divide then, because ujj, the diagonal element of u, is not equal to 0. And then we can use a nice notation. The notation would be aijk, and that's the element aij at stage k equals aij minus the sum up to k minus 1. So what I've done here is, you see an I here, a j here, and we can unify that and use a notation. aij at stage k equals this part. Okay, and we can use this new notation now, substituting I equals k. Then we get that uij, ukj actually, equals akj at stage k, because we substitute the k here, and we have, with this formula, we have the akj at position k. And similarly, if we substitute j equals k, then we have an lik, which becomes aik at stage k. And now we are already close to an algorithm, because if we can compute all these values aij at stage k, then at stage k we can retrieve row k of u and column k of I. We have now derived an LU algorithm, and we've seen that we can compute the U and the L elements in stages. And here is the complete algorithm with stage k equals 0 to n minus 1. And then we first retrieve the values from row k. These become the values ukj. Then we compute the values of L from column k. And then we update the matrix elements by subtracting lik, ukj, elements that we just computed, subtracting it from element aij. Now, this is an algorithm that's correct, but how do we understand that it really works? So one way of doing this is using a loop invariant, which we have seen before. It's a statement that tells you what the situation is at a certain stage. And the statement remains true while a loop is being executed during the iterations of the loop. And the invariant that we propose for LU decomposition is that the value of element aij at stage k equals the original element aij minus the sum from r equals 0 to k minus 1 lir urj. So this is a sum, and if we increase k, then the sum gets an extra term. And here we see the loop invariant inserted in the algorithm. So at the start of loop k, we assume that the invariant is true. Initially, for k equals 0, it's trivial to see that it is true. And then, assuming that it is true, we have shown that we can retrieve the correct values for for ukj and for lik. But then we must make sure that for the next iteration, the invariant also will be true. So that's why we subtract an extra term, the kth term, from the values aij in the part that is still relevant, and that's actually only for the lower bottom corner of the matrix. So for I and j larger than k. And if we do that, we establish the invariant for the value k plus 1. And then we increment k and we do the next iteration. So we have an L, a U, and a matrix AK containing the elements aij with a superscript k. And we see that every time we compute a column of L, a row of U, and we have some remaining part of the matrix that we update. And they all fit nicely into one matrix. And we call that matrix simply A. And that way we get an algorithm where the L's and the U's have disappeared. But we have only a matrix A. And the algorithm also becomes a bit shorter because we don't need to copy elements from A to U. So we first divide all the AIKs by the diagonal element, AKK, and then we update the matrix part that is still relevant. Now I have a question to you. This is the LU decomposition. Will it work for every matrix A? Think of a simple matrix. Well, if you try this algorithm on the matrix A, which is 0, 1, 1, 0, you see that the first element is a 0. That's a diagonal element where we're trying to divide by that element. So obviously the algorithm will break down immediately. So what's the solution to that? Well, instead of taking this matrix, we permute the rows. And we can still continue then with the LU decomposition, because then the 0 becomes a 1, and this will work. Formally, we say that we multiply the matrix A with a permutation matrix P. And then this permutation matrix, P times A, for this matrix we compute the LU decomposition. The definition of a permutation matrix is a matrix that you obtain by permuting the rows of the identity matrix. So a permutation matrix has only one in every row and in every column, and for the rest it contains zeros. Sometimes you don't know what the suitable permutation matrix, what it is. Then you have to compute the LU decomposition, and when you try to divide by 0, you permute suitably. And this is what the procedure is, what people do in practice. And then you permute it actually by moving the largest element in column K to the diagonal, so that you're as far away from 0 as possible. Okay, now we also want to know what the cost of this algorithm is. And for this cost analysis, it's very useful just to use two well-known formulas. The sum of all the elements from 0 to n, that's n times n plus 1 divided by 2. And we have something similar for the sum of all the squares from 0 to n. And we can use that if we want to see how many flops, floating point operations, we perform in the LU decomposition. So this is the time of a sequential, non-parallel LU decomposition. And we have stages k equals 0 to n minus 1. And in every stage, we first perform divisions for all those elements between k plus 1 and n. And that's altogether n minus k minus 1 elements. And we perform, for every element in the lower right-hand corner of the matrix, we perform two flops, because we perform a subtraction and a multiplication. So that gives 2 times n minus k minus 1 squared flops. So we add all of them up, and we can simplify this formula by just realizing that if k is from 0 to n minus 1, then n minus k minus 1 is also from 0 to n minus 1. So we can write it as 2k squared plus k. And then if we do some simple algebra, we get a formula 2n cubed divided by 3 and some lower order terms. So this is the cost of an LU decomposition expressed in flops. So a summary of what we do. If we want to solve a linear system, then it is best to perform first an LU decomposition. As output, you get a matrix P, which is a permutation matrix, an L, which is a unit lower triangular matrix, and a U, which is an upper triangular matrix. And then we permute the right-hand side into PB, and then we solve Ly equals PB and Ux equals Y. And this costs about 2/3 times n cubed flops. And each triangular solve is a lot simpler, a lot less costly. It's only n squared flops. A final question to you. Now that we have an algorithm, try to compute the L and the U for the matrix A, which consists of 2, 2, 2 in the first row, 2, 4, 4 in the second row, and 2, 4, 6 in the last row.